Assalamu alaikum. Today we will discuss about the eigenfunctions and linear time invariant system. Consider a linear time invariant system, that is the LTI system, with the input x of t and the output as the y of t. So usually the LTI system is usually represented as h of t. That means you have the input x of t and the system as h of t, and the y of t is given as x of t convolution h of t, which is nothing but integral 0 to infinity x of t minus tau into h of tau d tau. So this is by the definition for the convolution. Now consider some special functions. These functions are known as the eigen functions. So consider the special function. Let us assume that our x of t is equal to e power st. Now let us pass it through the system. Then you will get the y of t as integral 0 to infinity x of t minus tau, that means e power s t minus tau into h of tau d tau. I can write this in a different way, that is my y of t is equal to e power st into integral 0 to infinity e power minus s tau into h of tau d tau. So you can see that I have taken this e power st outside. Actually this e power st was the input to the system. You can see that it is appearing here without any change. That means I can represent my y of t as e power st multiplied with this term. This term will be a function in s. You can see that we are integrating it over tau, and this will be a function in s. So I am going to write it as h of s. So I will show it in the next page. So my system was like this, h of t, and I give the input e power st, that is my x of t, and I got the output as y of t, which is nothing but e power st is, again you see it is repeated here in the input as well as the output, but it is scaled by a factor which is h of s. So this kind of function which are appearing in the input, and it will get unchanged. There won't be any changes in these functions even at the output, and this kind of functions are known as the eigen functions. So this is the eigen function. So you can see here I have the eigen function. This is the eigen function. I have given this eigen function as the input. I got the eigen function as the output, which is multiplied with some value, and this is the eigenvalue of the system. Eigenvalue of the system. So h of s is the eigenvalue of that system. Now let us consider the same system h of t. Since we are considering the LTI system, let us consider the input x of t as e power s1t. Then what will be the output? My output y of t will be e power s1t multiplied with h of s1, isn't it? Now let us consider my input x of t was e power s2t. Now what will be my output? My output will be e power s2t into h of s2t. Now since this is a linear system, let us give the input as something like a into e power s1t plus some b into e power s2t. That means we are combining the above input as the new input. Okay, so this is the case 1, this is the case 2. Now we are discussing case 3, which is a combination of the others. So what will be my output? My output y of t will be a into e power s1t into h of s1 plus b into e power s2t into h of s2. So this is my output, right? Now let us give the input in general. I am giving the sum of many e power STs, that means e power SITs, into, that is, if I give like this, my output y of t will be the sum of e power SIT into h of SITs. Okay. Now suppose if I am scaling with some factor, so this is my x of t. Suppose if I am scaling this with some factor x of SI, then the same thing will be reflected here also, x of SI, because this is the scaling factor. You can see this the third case. It is same like the third case. Now if I am giving a signal x of t which is a combination, that means here in the above fourth case actually I have considered only some discrete values for SI of t. Sorry, not SI of t, it is discrete values for SI. Now I am considering all the continuous values of, that means I am considering all the combinations of ST. That means I am multiplying with e power ST into x of s, and I am integrating this. Instead of summation, I am using the integration. That means I am combining all e power st, and the coefficient is e power xst. Then what will be the output? The output, instead of the summation, I have the integration. Then e power st will be reflected, because I am giving the input as e power st, so this will be reflected here, into x of s, okay, into h of s. So I forgot to represent in the x of t, I have forgot to represent the integration variable as ds. So here also at the output the ds will appear. So you can see here, I will explain in the next page. You can see here I have a system now, h of t with the input x of t, which is the combination, that means it is the summation of some coefficients x of s into e power st ds. Then what I am getting as the output, my output is like, you see here my output is like e power st is there, so I will write e power st here, my e power st is there, then x of s into h of s. So I have x of s into h of s, and the integration variable is ds. Now you can see here, this is the eigenvalue of the input signal, and this is the eigenvalue of the system. So you can see this is the eigenvalue of the input signal, eigenvalue of the input, and the system is having the eigenvalue h of s. So if we consider only what is happening to the eigenvalues, means at the input side you have the x of s as the eigenvalue of the input, and on the system side actually we have h of s as the eigenvalue of the system, and we can see the output is my x of s into h of s. This is actually, we are actually multiplying these eigenvalues at the output side. So this is what happening if we are seeing what is happening at the output. So this we will define as y of s. Now we can define this term x of t. Now you see here our x of t is actually x of s into e power st, or I can define my x of s. Actually I am not going to prove it here, maybe we will discuss it in another video. X of s as x of t, this is the integration limited from 0 to infinity, sorry for this, 0 to infinity. So 0 to infinity e power minus st dt. That means to find this eigenvalue of the input, we need to integrate our x of t after multiplying with e power minus st, and we are averaging it over time. So this is nothing but the eigenvalue of that input, and this is nothing but the Laplace transform of this signal x of t. So what we can see here, that we have the h of t as the system and x of t as the input and y of t as the output, which is the nothing but the convolution of x of t with h of t. But in Laplace domain, we have x of s as the Laplace transform of x of t. We can say the Laplace transform LT, that means the Laplace transform of x of t. And if we take the Laplace transform of this is nothing but y of s, and if we take the Laplace transform of h of t, which is the h of s, so which is this is equal to x of s multiplied with h of s. So you can see here that this convolution is changing into the multiplication. So the convolution in time is changing into Laplace transform. If you take it, it is changing into the multiplication. Okay, so the convolution is changing into multiplication in Laplace domain. So you can see now that there are some functions, that is what we have defined. There are some function e power st, and suppose h of s is the Laplace transform of h of t, then my output y of t is nothing but e power st multiplied with something h of s, where h of s is the Laplace transform of h of t. So you can see here that my input is e power st, my output is also containing e power st. That means that function got unchanged. So the eigenfunction are the functions which are not subjected to any change. So only it is scaled by some factor h of s. So this kind of functions are eigenfunction. So I hope that you understood the video. You can also try with cosine omega t or omega naught t. The same results you will get, but the signals will be represented in terms of cosine omega naught t. But here the signals x of t is represented in terms of x e power st. I hope you understood the video. Thank you for listening.